Hello, are you able to hear me? Hello, are you guys able to hear me? Yeah, let me share my screen. Um, Please let me know if you can see my screen. Okay, let's start with today's topic. That's abstract data structure. Yeah, so let's start with today's topic. That's abstract data types. So, what is an abstract data type? Let me clear it to you. So, an abstract data type is something where you can implement it.
It's the screen share is turned off.
Oh,
yeah.
Just give me a second. Yeah. Are you guys able to see now? So, an abstract data type is actually a theoretical concept in computer science that defines a set of data values that can be performed using on those values. Like if you implement a queue in data in Java, you'll implement it, but you won't be able to see the operations behind it. Just like how does it perform all those things, like pop, poll, add, or some other types. That or top and just like peaking on the value, like which is the top value, so you won't be able to see those values in Java. But yeah, so that's abstracted, right? You can say that's been encapsulated. So the performance, I mean the implementation is encapsulated. So there you can these are the common ones, which are the abstract data types, just like list, array list, linked list, and just like if you declare a list here, you will be able to access this list by using my array list, because that's the name of the variable you set to that's the name of the variable you set for the new array list. So every time you want to access this list, you'll be able to just use it by this accessor. And the for the just like imagine if you declare a class, you just give a constructor, so some getters and setters methods, so you want the user to just use those things based on the getters and setters, not like get the original data values. So that's main use of abstract data types, which will perform. They are just like basic things which is used to like encapsulate the other operations and just give you the results. So that's basically what I said. Like it's more of a container type. Just like here the constructors here. So if you make a list, you can have a constructor called empty list that will return an empty list, or make list using an element. So just like if you have an array list in Java, you add just like you have a method called dot add. So list dot add, so it appends a value at the very end of the list. So you don't know how it is, but it is working in the memory. So the method which Java is using to add the value to the end of the list has been encapsulated, but it's getting added. So you don't know how it is, but it is working. Accessors method, just like first returns the first value of the list, rest returns the rest value of the list. So let me show you one thing. So it's loading. Yeah. So if you have a list like this, that's a kind of a linked list, which has a, let's say it's a value of 2, 6, 9, and 10. So when you do list of first, that is, it will return you the 2 because that's the first value. And if you do list dot rest, so it will return this value. So your head will be like a temporary head will be here, or you can say a temp. It will return this temp here, because because this is also a list, so that will return a list type. And if you do list dot end, that means this value, so it will return 10. So that's how these are working. But in memory, it is most likely some, if you consider this is a memory. So um, this is for a linked list. It can be for anything. It can be for linked list as well. It can be even for stacks, queues, graphs, or hash maps or something like that. Because you don't know, like how is it? Because imagine like if you declare an array, so all the array is contiguous in memory. But when you declare those list types, so they are scattered all around the memory. So whether so this list could be like a two node is here with an address which is like, let's say 50, and it is pointing to a 6, that is 6 here, which is the address of 50 here, but it will have another address like, let's say 90. It will be pointing to the 9 here, which will have an address of 90. So when you get start on adding it will just add the nodes anywhere in the memory with just with the location, because these will the memory location pointers. So you don't know how it's getting implemented, but you know it is getting implemented because of the memory data structure type. That was all for abstract data type, but yeah, it is not only for list. It can be implemented for hash maps, queues, graphs, or any other data structure which you can make. Like even though like if you make some classes, like just say class of you made a manual linked list using a class node, and you made a list of, or say hash map of node comma integer, so where each node will have point to an integer, but that won't be like in the memory like continuous, so it will be scattered all around the memory. That's the operation which I told you, like using in the list, like list dot last return list and else return. So this says like if the list is empty, it will return an error. So if you have an empty list, it won't return anything. Or if it's not empty, so it will return the first of the list, because first or the last, and then it will return the last of the rest of the list, because you are having the function last here. So get element by index, this one. So this one basically works like get element by index. Let's say you have a list here. Let's say 1, 2, 3, 4, 5. So let's do a zero based indexing for it. 0, 1, 2, 3, and 4. Um, so it says, okay, if you want to access any of those by index, just say if you, right, if you want to access the first node, what you need to do, because your head is here, so this is head dot next, or this is the next pointers. If you want to visit the first node, I'll do it iteratively, because recursively you can also do it, but iteratively is much more beneficial, because so you just declare a temp pointer which is at head. So there is a temp pointer. You declare a while loop. That is the temp.val, because if you know a structure of node, it is something like int val and a node type of next. So while temp.val is not equal to, or you can't you don't need to do it like that way. You can do it like, if you want to access the second one, for int I equals to 0, I is less than equal to 2, I plus plus, I mean less than 2, because it's a zero based indexing. You do temp equals to temp dot next. So what we'll do is you are here. So at first I is 0, so temp is here. When you go to here, then I is equals to 1. 1 is less than 2. It will stay at here now temp. Now second iteration, temp will go to temp will try to go here because I will be 2, and it will exit out of the loop. So your temp variable is here. So after that you return temp dot val. That's the iterative way to go to the list with the number. That will give you the second node. Is it clear? Yeah. And append. So append generally adds a value to the last of the list. So generally you can add to any position, but preferably in list it adds to the last position. So what it does is, if you think about a list here, you have a linked list here. Let's say 1, 2, 3, 4, 5, 6. So these are all the next pointers. So 6 next pointer will be pointing to null, right? Because it's a linked list and there is nothing after that. So your head will be pointing here. And let's say you want to add a value called, like, let's say 90. That's the value to be added. First, you create a node of it. If you haven't created a node, then you create a node of it just by using the constructor. So the constructor will make it a node, like having a node 90, which will point to null. So you iterate on the list basically, while let's declare a temp, because the thing why I'm declaring a temp, because if you start moving the head, you will lose track of the head, and if you lost track, you can't access the list again. So you need to declare a temp. So a temp will be pointing here. So how to go here? While, so this thing is null, right? So we can do while temp dot next is not equal to null. You can do temp equals to temp dot next. So temp will be here first. We will try to go here. Is temp dot next not equal to null? Yeah, it is not equal to null. So temp will be now here. After the temp will be here. After the temp will be here. After the temp will be here. And after that temp goes to here, it checks if temp dot next is not equal to null. But it is equal to null, so it will break out of this loop. So your temp is pointing here now after the loop. So this is the next pointer of the temp. This is the next pointer. So you just point the temp's next pointer to this node. So how do you do it? So if you created a node, so you have given it a name, let's say node A. So you just point temp dot next to A. That's it. That's how you add it to the list. That's that's adding to the ending. But where if you want to add a list to the beginning, let's say you want to add, let's do it again. If you have value 1, 2, 3, 4, and you need to add a value called 90 to the head of the list, to the front, that could also be a possibility. So how do you do it? Your head is pointing here. You create a temporary node for this, let's say node A. So first you point node A's, and that's the next point. That's the next point, which is pointing to null. So what you do is you make this pointer pointing to the head. So A dot next is equals to head. So your list is connected, but your head is over here. So even if you try to access this, you won't be able to access it. So you need to move the head. So head is equals to A. After that, your head will be transferred to here. You guys understand that? Um, did you guys got it? I'm taking that, yes. Okay. And there could also be a condition where you need to add a value in the middle. So that is like 1, 2, 3, and a 4. And you need to add, let's say, 90 to 0, 1, 2, 3 on the second position. So you want 90 to be added to the second position, second index. I'm following a zero-based index here, so I want 90 to be here after 2. So that means what I need to do is I need to go on to a for loop while your head will be pointing here first. You create a temporary head so that you can iterate on the list through that. So you create a temp, you move the temp until you reach that index. So an index before that, not to that index. So when you reach 2 here, your temp will be pointing here. You break out of the loop. You need to point a next pointer so that you can track of this list. So because when you change this pointer to here, you'll lost track of this list. So you need a next pointer to track of this list. So let's say this node as a. So temp dot next is equals to a. So this pointer goes from here to here. Now you need to place a to that. So a dot next is equals to next, because that was the name of this. So and that's how this node gets added in between. That was like yeah. So they made a make list, so which we did in the last one, um, in the linked list. So they used that function here. But yeah, that's all iteratively done here, and that's all for list operations. I mean abstract data types. Let's move on to stacks. Is it clear now? Any doubts? Let's see. All good. Okay, so let's move to stacks now. Mm, stacks, yeah, there you go. Okay, so stacks is also abstract data type. So there are three operations, but okay, so you can add a value to the stack, you can remove a value from the stack, but you won't get like you won't be able to access the stacks class. So that's why it's called an abstract data type, because you will be just able to do the operations without any kind of seeing like what's going inside. That's mainly encapsulation which is occurring, where the interface is being hidden by the user. You just get to use the functions. But yeah, so stacks is a leaf for one, so it's last in first out. You have three operations, that's push, pop is empty, and also one more which is we can take out the top. So let's go to Miro again and let me tell you how stacks work. So stacks are something like this. Imagine like this is type of container. You have a value like 3, 4, 5, 6. You pushed 3 inside, you pushed 4 inside, you pushed 5 inside, you pushed 6 inside. So for pushing the values inside, you use a push function. Let's say push of x. To remove, okay, so after that you can't access the from here. You can only pop from here. So that's pop. Pop of x will remove the value which is at the top. Also there is one more which is called top of x, or generally in Java it is called peak of x. So peak of x won't return the won't take out this value out of the stack, but it will just see the value. Let's say an I is here, so you'll just be able to see this value and it will return the value number which is there. Whereas when you use a pop function, it will just remove the value from here and you'll have in a variable, let's say int k equals to pop of x. When you did pop of x, it will, after that k will have the 6 because it will be removed from the stack. That's how stacks work. And also one more function, yeah, stack empty. So if the stack is clearly empty, so it will return true. Otherwise, it will return false. Generally, that's used for empty one, or it will return an error because if you try to pop out of an empty stack, it is not possible, right? So it will give an exception. Yeah, that's all which I told about. Yeah, some one more thing. This one. So imagine if you pushed a value inside a stack, let's say 3, and then if you run that function is empty, it will always give false after pushing a value. Because you push the value and the stack is, or if it's empty, it will eventually have a value. So that's why it will give a false. And next thing, suppose this is just the example. Okay, so that's the example like where stacks are used. So if you have like some task A, B, and C. So if A is dependent on B and C, so you push B and C. But if C is dependent on D, so you then push D, and then you can pop everyone back. So that's how the tasks are solved here. Um, that's just more example on this. Another example is the evaluating writing in reverse polish notation. So yeah, reverse polish notation of stack, it is like, let's say if you have certain numbers like 3, 6, 7 minus 5 star. That's it. Let's do it here. So first you do is you push this value 3. After doing a pop, does that means the element of the stack? After doing a pop, where does the element of the stack go? You can store it in a variable, or it just gets out of the stack. Either you can store it in a variable, or if you don't need, you can just do a pop. It is removed from the stack actually. Is it clear now? Uh, yeah, I'll take that. Yeah. So reverse polish notation is when you push the values, like if you got a set of values like using stars. So you push 3, after that you push 6, after that you push 7. So after that you encounter a negative sign. What does that mean is you pop out 7, you pop out 6, you subtract it. That will result in -1. And you push that back. So it will be like, after that the stack will look like 3 -1. Because you pop 7, you popped 6, you did this -1, and then you push the result back. After that you encounter 5, so 5 comes here. You encounter a multiply sign, so you pop out 5 back, you pop out 1 -1 back, you times them, so that gives -5, and then you push it back into the stack, so it'll be like 3 -5. So it is like when you encounter a sign, you just check the ADT of the signs, like how much how many parameters it will take. Like generally each one takes like one, but there can be like certain kind of predefined function where user defined function where it can be like sum of three, just like will pop three values. So it will pop the values out, it will perform the operation, and then it will push it back into the stack. So that's reverse polish notation. Stacks are heavily used in applications that involve exhaustive search of some problems. So stacks, one more implementation of stacks is when you call recursive functions. So when you call recursive function, they create a stack in your memory. To reverse a stack, would you just keep popping and placing it into a new stack? Would there be reversal? Um, you probably need another stack to reverse that stack, because when you reverse a stack, you just pop out back. So let's say if you have a stack like this, if you have something stack like 3, 6, 7, 8, 9, 10, you want to reverse it, but uh, you can't like access like pop 3 back, or you can place it here because the pop only happens from the top. So you just need another stack where you pop 10 out, you push 10 here, then you pop 9 out, you push 9 here. And that's using a variable because you're doing int x equals to, let's say this is stack 1 and this is stack 2. Int x equals to stack 1 dot pop. What data type is each element? Each element, is it a node like a linked list? It can be anything. You can have a stack of integers, you can have a stack of boolean as well. Yeah, you can have a stack of list node or any custom class which you made. We can make, because stacks are generally like you need to specify what type of value you use to need to use, because there you need to specify either int or node, or you can use a tree as well. That will be a tree node as well. So stacks can be anything. You can have anything in the stacks, and that was I was talking about here. You just pop one by one and then push it into the new stack, and then it will be reversed. I hope that is clear now. Is it clear? Yeah. Okay. Next thing, stacks ADT, that is empty stack, push, top, pop, and is empty. So empty stack will return an empty stack. Okay. Let me go to Miro. Okay. So these are the identify which I again mentioned you at the very first. Like if you have a 3, 4, 6, 9. So pop of x will give you 3, but it will remove the element from here. If you do a peek, that is top of x, now x is here because you remove the 9. It will give you the 6, but it won't remove from the stack. And one more is stack dot is empty. Yeah, stack itself. Yeah, yeah. Or you can either write is x dot pop or x dot top. Or stack dot is empty will return if the stack is empty or not. If it's empty, it will return true, and if it's not empty, it will return false. And you can use a push, which will push into the top of the stack. Stacks as linked list. Okay, I have made a program on this. I will show you after I finish this slide. Actually, stacks as linked list. Okay, let's have a linked list. Let's say, let's consider the example above. Um, 3, 4, 6, 9, and this is pointing to null. Right. So let's assume the order of the elements which came in was 3, 4, 6, 9. So how will it be in the stack? It will be like 3, 4, 6, 9. Your head will be here, right? So if another number comes in, let's say you pushed in a 10. So what we'll do is you create a new node that is 10. This null goes from here to here, and this points to null. Does that make sense? And that's the push operation which you do is just connect the next pointer to the new value or making a new node of it. There could be a pop operation as well where you want to pop. So when you want to pop, it will return the 10. So how does that occur? So you traverse the linked list from here to here to 9, set the next pointer of 9 to null. If you can do that, that will return that value. So how do you do that? You have 3, you have 4, you have 6, you have 9, you have 10, and your head is here. You create a temporary pointer pointing to the head. Okay, so stacks always occur on the last value. So you do, you need to do like, you need to traverse the temporary pointer till here. If you can somehow go the temporary pointer to here, you can have another temporary pointer temp2. You need this temporary to just to return the value. If you don't need to return anything, then you can just don't have it. So you just need the temporary pointer to just return it. You can set the temp dot next to null. So what it will do is it will cancel this one and it will point to null. So this will free up this thing. This node will be by alone, and then you can return temp2.val. But how does this? How do you implement this? That's the question. So you can do while temp dot next dot next is not equal to null. You can do that. So it will check the next pointer. So it will check this. So it will always finish up in the second last one. If that is not equal to null, so you can do temp equals to temp dot next. So this will assure that your temp goes into here. After that, you can have a temp2 is equals to temp dot next. This will have a temp2 value here. Then what you do is temp dot next is equals to null. So you set that to null, and then you return temp2 dot val. That's the value which you want to return. That's why you use a temp2 here. Otherwise, if you don't need to return temp any value using the pop operation, then you can just have it using that. I hope that is clear now. How you can have it uh, use the pop operation and push operation and the is empty operations. Let's suppose if your linked list is empty. If your linked list is empty, so your head will eventually point to null if your linked list is empty. So you just check if head is double equal to null. If head is double equal to null, that means it is empty. You just return true. Else, return false. That is how this works. The is empty function. So you learned about pop operation and the top operation is left. I mean, you did pop, push is empty. So top operation gives the last value always. I mean, that's a linked list. So if you want to get the last value, you can just iterate on the linked list while temp dot next is not equal to null. You can just iterate on the linked list temp equals to temp dot next. So it will eventually go into the last node here, and you can just return temp dot val. That will return the last value, but it won't pop. Is that clear now? All the operations? Yes. Okay, so one more implementation which you can do is, right, one more thing. See how, how you are traversing the whole linked list. So it is taking an O of n complexity because you are having a for loop or a while loop to the end. So is there any, you should download OBS, it's really good. Yeah, I will for the next stream then. So let me tell you, like, here you are traversing the whole linked list while adding or deleting a value. Like it is taking an O of n complexity if you are doing it with manually. So if you're doing it in Java or C++ or something else, any other language, it will generally have an O of 1 complexity. But here you are applying it by manually, so you are having an O of n complexity because you're traversing the whole linked list, and then you are changing the pointers. So is there an efficient way? Probably yes. Let's see how we can implement a more efficient way. Let's say if we have a stack here with a value 3, 4, 6, 9, 10. What we were doing is we're making a linked list like 3, 4, 6, 9, and 10. And what we were doing is we are adding to the end here, or we are removing this pointer. What if we try and make it like this? 10, 9, 6, 4, 3. So the linked list head is here, just reversing the order. So if we want to now add a value to the stack, it will be just like if you just say if you want to add a value called 90, you'll just create a node of 90. Let's say the node be A. So that's a node now. You create a node. You just point, it is pointing to null. You just need to change this pointer to here. That's node A. A equals to head. That will change this pointer to the head, and you just shift the head to here. Head equals to A. Remember, the ordering matters because if you do head equals to A first, then you will completely lost track of the list because you'll have a list, you'll have a node by itself, and you just point it to itself, to that one. You'll just completely lost track of this list. So the ordering matters here. So that will take O of 1 complexity, time complexity, because you don't need to traverse the list. You just change the pointer. And if you want to just pop out the value, just say, let's take this example only. 10, 9, 6, 4, 3. Your head is pointing here. You need to pop value. So you can have a temporary pointer here. You can just move the head over here, and you just point the temps next to null. What it will do is it will change this pointer and it will point to null. Now you have this list by itself. That will take O of 1 time complexity. Eventually, here we are doing is we are traversing the whole list and then we are adding at the end, and we are traversing the whole list and we are removing from the end. We can just have it at the very beginning. We can just add or delete from the beginning, and that will take just by moving the head, and that will eventually can reduce less errors as well. Does that make sense? Okay, yeah. Next thing. Uh, Yeah, that's what I was talking about. The second operation that will mean push equals to insert at end. Eventually, that the second one is so the second one option is not reasonable. That is having the top at the end, having the top at the beginning. So that's what I was talking about. Like if you reverse the list, it'll be much faster because you will be just pointing with the head. Stacks or arrays. So you can have a, yeah, just like we did it using the linked list here, we can implement using an array, a stack, just like you can just push the values. Like if you have an array like ARR, It will be like, let's say, obviously you need to specify how many was the size of the array, because you can't have an infinitely array. That's because of the linked list. You can have an infinitely long linked list. But yeah, for an array you need to specify. Let's say you have a array of size 5. Initially, you initialize them with all with -1. Let's assume our stack doesn't have any negative value. So that will be the front here pointing. So you just check if it's -1, then you push it inside and push the value inside, and then you increment the front. That's like more easy. And if you want to remove a value from the array, you just change it to -1 and then decrement front. That's what we were doing here. Just like a more easier way. Let's say you have an array all with -1, -1, -1, -1. Your front is initially pointing to 0th index. You push the value, let's say 5. This will become 5. Then your front will change to 1. Then you again push the value called 6. Your front will change to 2. Front will be like which value is free. And then when you just want to pop it back, you just change it to -1. And then decrement your front. That will do the array one. Does that make sense? Yes. Simple enough, yeah. Storing arrays has an advantage as we avoid calling allocate memory all the time. Yeah, that's true, because if you're using arrays, so it will have a contiguous one and you don't need to traverse and have pointers and stuff in the array, because array are just contiguous blocks of memory, and that will be much easier. But yeah, so the one disadvantage of array I would speak about is because you can't have the whole array filled. Uh, like imagine if you have an array of size 10 and you got like three of them filled, three indexes filled. You got the array, rest of the array as unfilled. So that will set up in the memory taking up no space. That will be like uh, that's actually bad. So that's why you want to implement it using a linked list, because linked lists are much like can be placed anywhere in the memory heap. That's what was the array one. And in Java, you can have a class library using the DQ, which is actually used both for stacks and queues. So let me tell you about what DQ is actually, or I'll tell you about after the queues one. If you want to see how stacks are implemented, let me show you how I implemented stacks in Java. Mm, enter the stacks. Yeah, I got the implementation using the linked list as well as using the arrays. I mean, um, reopen circular key. No, it didn't. It is loading. Do I need to open IntelliJ? Yeah, new window, new window. That's the implementation using linked list. Okay, so classic thing, node, which will have a data, which will have a next pointer. You have a constructor here, which will initialize the data and the next to the null. That's what I was doing here. You have a stack class. You have a private node head. So you initialize a head. So see, that's abstract data type, because when you go to the user main function, you will be just able to use push, pop, print, and other stuff. You can't access those, because if I go here I'm having like some other kind of methods as well which can go around. Just like if I using a push function, it could eventually call another method which the user won't know. The user will know because I'm pushing. It will call the push value. So what push does is it adds data to the end. So data to the first because we did it on the effective way. So it adds data to the first one. You make a node of it. You make that node point to the head, and you just make it to the that node head. Pop if head is equal to null, so if there is nothing in the node, so in the list, so you just print stack is empty. Otherwise you shift the head. That's it. I'm doing it as a void here. Otherwise, if you want to be an int, you can just return head dot val, and then you can just make it to the next pointer. In peak, that will give you the top of the stack, so it will return head dot data because data is the value which contains the data value. Is empty. If head is pointing to null, then you return true, otherwise false, and that's a print statement. That was using the linked list, and this is using the array. So the thing with the array is array and linked list is, see here we don't have a specific size, but here we had to specify a size of the array. That's using like more blocks of memory if it's unused. And also if you like you need more memory in the stack, you can't change it because once you declare the stack, it will be of that much size only. So you declare an array with size, you just make the top with -1, or you can initialize all of the array with -1 using arrays.fill method. When you use a push, so if size minus top is greater than 1, so that means it checks the overflow condition, like if the stack is not overflowing and your head is like the front is at the very end. So you just do top plus plus and you add the data into the array. When you do a pop function, you just decrement it, or you can set it to -1 as well inside the data. And using the peak, you just return the array of top. See here, the top is constantly getting incremented when you use the push function, so that the top will point to the next free location. I hope this is clear now. Stacks. Is it clear? Yeah. Now let's go to queues. Okay, so queues are first in, first out, which is FIFO. So let's talk about queues first. On to Miro. Let's go to Miro. So first things first, where queues are used, like if you have like some task in memory which have like which needs to be processed on the based of the order which they comes in, so their queues comes into play, where the first thing which comes is served at the first one. So that is mainly, or otherwise you can have a priority queue because you have a priority assigned to each of them and where it will be sorted according to them. So we will talk about later using the priority queue. So what queue is, you can say it is a kind of linked list only, where it is like this. Let's say that's 1, 2, 3, 4, 5, 6. So in the stacks, if we had 1, 2, 3, 4, 5, 6, if you wanted to pop out, 6 will get popped out. But here in queues, 1 will get popped out. Very simple. You just move head to head dot next. You just move the head to here, and that's popping out of the, that's called DQ. Eventually you can just imagine it like when you did the stacks one using the other side one, this one, you can consider it like a very similar version of it. So NQ adds let's say 1, 2, 3, 4. NQ will add a value to the very end of the queue. let's say here, dq will remove the value which is at the front. That means your head will now come here and it will remove this, because it will eventually get processed in the order which it comes, like this packet, this packet, this packet, this packet. You want to add a packet, so the packet will come here, the new packet one. And if you want to remove, this packet will get removed because it's at the first, because it came first. That's mainly, and also you have is empty function which will check if the queue is empty or not, and if it's empty it will return true. Yeah, NQ rear front. That's and DQ is from the front. That's what I was talking about, because you remove it from the front, and NQ you just push it to the end. And if there are no values in the queue, it will eventually give out an exception or error, because you can't take or pop values out of a queue which is empty. So queues are also an abstract data type, where you will implement those methods, but you don't know like how is it getting implemented. It will be like in Java, it's like an interface where it is implemented. Starting from an example of an empty queue 4 3, then DQ1. What is the last value you get? Okay, let's do this question. Starting from an empty queue, so initially my queue is empty, then you NQ1, NQ3 and 4. Initially it is empty, UNQ4, after that UNQ3, then UNQ1. This is the order which we are following. I mean, this is one. Then you DQ it 2 times. So when you DQ it, you remove 4, you remove 3. So you just remove them. Now there'll be just one which is left. DQ 2 times. What is the last value you get? That is 1. That's the last value which you'll get. And what will happen when you DQ next time? So, okay, so I read the question wrong actually. UNQ4, UNQ3, then you DQ1. I just forgot this DQ here. So you DQ, so when you DQ, you just remove the 4. Then you NQ1. Then you DQ twice. So when you DQ twice, you'll remove both those two values. So your queue will be empty here. And then when you try to DQ it again, it will give you an error because queue is empty. Does Yeah. Okay, next thing. Queues are useful when we have to process tasks in order. That's what I was talking about. When you got like some kind of tasks which are there in the memory, like which needs to be served in the order of first come first served, then the queues are much more useful. Queue ADT. You have empty queue. That's what I was talking about. Push elements to the front of the queue. Top, and that's give the front element. Pop, and that's DQ, and is empty returns whether the queue is empty or not. That returns true if the queue is empty, and it returns false if the queue is not empty. So queues as linked list. One more thing, DQ here. I'll talk about. Yeah. So DQ is like you have a queue. Let's say you have 2, 3, 4, 5, 6. In DQ, either you can add it in the front or pop it from the front. Add, pop. Or you can add it to the back. Or you can pop it from the back. So it's a doubly-ended queue, you can say. Or more likely, you can say it is a type of linked list only, because you just add it from the front and the back, and you just pop it from the from the front. Also, you can pop it from the back as well. If you want, let me show you the Java one for this. Let's create a new project. Uh, DSA main function. So if you're using Java, then you can have a DQ interface here. That's the type of specifier you need to want. So probably an integer type. I'll call it as q equals to new. So that's an interface where you need to implement the methods by yourself, or you can have a linked list or array DQ here, because that's if you use linked list, all those things will be hidden from you, like the operations. Or if you wanted to implement by yourself, then you can use a Java, like the interface here. So here you can see like the function which you have q dot add first, add last. That's add to the first and add to the last. Or you can have Paul first and Paul last. Paul means to pull out the